that, let's talk about circuits. The point of this is just to give you the basic idea.
I can sit over here and hit the next button if you want. Might be on the other screen.
Hit me.
Can I just hit you?
I think so. I think that's the idea. Okay. Yeah. Ken, yes, it is. I'm gonna work on that. Right. Is that what you want?
Yeah.
That is what I want to. Hey.
That has some stuff.
Oh, yeah, in fact, do you mind making it and just like put it downstairs?
Put it on the table.
Basically, the point of this is just for me to explain the basic concept and the basic words that you're gonna see when you're dealing with circuits, so that as we go through the different projects, you can have an understanding of what's going on. The main three things that I want you to know, at least to sort of understand what is going on with a circuit, are going to be voltage, current, and power. That's going to come up in everything that you do with electronics. The way that I like to, the way that I like to think about those three concepts is that in every circuit, you have those little packets of energy that are moving around, and as they are moving through the circuit, they are what makes the circuit go. So if there's a light that lights up, it's those packets of energy that are making it light up. If there's something that's moving, that's how that's happening. And every one of them carries a certain amount of energy. And as they are moving through the circuit, current is what describes how many of them are moving in a given amount of time. So high current means that lots of bits of energy are moving through the circuit. Low current means that only a few bits of energy are moving through the circuit. Yes.
Election, so it gets me. Is it current is the same thing as amperage?
Yes, current is measured in amps.
Okay.
That's named after Ampere, some guy that figured out how current works like 200 years ago. But yeah, and if you think about the fact that current is really describing how much energy, how many packets of energy are moving through the circuit, that means that lots of current, lots of energy is potentially dangerous. Not enough current means that things are not going to work. This is why you have things like circuit breakers. So in your home, what a circuit breaker is doing is it's limiting the amount of current that can go through your wires at any point in time. Yes. And the other measurement that we have in the circuit is called voltage. And what voltage describes is how much energy is in every one of those bits of energy that are moving through the circuit. It's measured in volts, as you might imagine. And just like too much current can be dangerous, too much voltage can be dangerous as well. Usually, once you get above 60 volts is when you really need to start worrying about safety. Everything that we're going to do here is going to be way below that. But one thing that's worth knowing is that voltage that comes out of the wall in your outlet is higher than that. So anything that involves circuits that are, touching the current from the power from the wall is potentially dangerous. And that's why a lot of things that we do in kind of basic electronics is either power from batteries or power from other power supplies that have lower voltage in them. 1 second. Yeah, we're good. And those two things put together describe how much power is in the circuit. So basically, the way that this works is that current is how many bits of energy are moving, and voltage is how much energy is in every one of those things. And then power is those two things combined. So more current means more power, more voltage also means more power. If you think about the meter that you probably have somewhere in your house that tells you how much you need to pay for your electricity, what that meter is doing is measuring how much power you used for how much time, and then it gives you an electrical bill based on that. Yes.
Is a circuit breaker something that will lessen the current that's go through, or does it just monitor for a certain thing to be surpassed and then
it just cuts it off? Yeah, it just cuts it off. That's why if you've ever had to flip a breaker if it tripped like that, the switch just switches completely off.
So when I was swapping outlet or light switches last week,
Uh-huh.
and I unintentionally touched two lives together,
Yes,
and I just took the whole thing. That was the breaker.
that was a breaker that it sensed too much current and then it
Okay,
disengaged. Yep.
Oh.
Yes, and we'll talk a little bit about like why this is bad and what kind of things, what kind of problems it can cause. But for now, all you need to know is power is energy moving through the circuit, and it comes from how much current there is and how much voltage there is. So in its most basic form, a circuit looks like a power source, which in this picture looks like this battery at the bottom, and a loop of wire with something attached to that wire. In this case, we got two light bulbs, and these little things that are wiggling around are showing you these packets of energy that are moving through the circuit. In order for a circuit to work, what has to happen is that this energy has to move from the source through whatever is doing the work, whether it's a light bulb or a motor or whatever it is, to a magical place that we call the ground for kind of pointless historical reasons. Also known as it moves from the positive to the negative. And this is not particularly helpfully drawn on this, but the idea here is that
It is a touchscreen.
yeah. Oh, yep. I've actually like it's you get close to it and it starts moving. Yeah. Yeah. So a circuit doesn't work if you don't have those three parts to it: a place from which energy is coming, the place to which the energy is going, and a path between those two that connects to a thing that needs to do some work. So that means that there are a few different ways that circuits can fail. And one of the most common ones is if you make an open circuit. So here you have a battery and energy could move into these bulbs, but then it doesn't have a way to return to the battery. And that's basically like having a garden hose that you pinched off on one end. And water is not going to go, water is not going to flow through it. And similarly, energy can't move through a circuit like that. And then these light bulbs are not going to turn on. There are more exciting ways to break a circuit. And the more exciting ways to break a circuit are something called a short circuit. And the way that a short circuit works is that you have paths where energy can go through your circuit, but those paths in some way are cut short or they're not going through the devices that you're expecting it to go through. So here on the right is an example of, sure, there is a path that goes through all of these bulbs all the way from one end of the battery to the other, but there's also a path that goes just from one end of the battery to the other end without going through the bulbs. And what's going to happen in this case is that this energy is going to decide that it's much easier to not bother going through the bulbs. And so you have all this energy flowing through this one tiny loop of wire, and that's called a short circuit. And it's problematic because it can catch fire, hence the fire in the picture. And there are other ways that you can make a short circuit. So for example, here, you have this energy has a way to go from through one bulb and then back to the battery. So it's going to look at that and be like, I don't need to go through the other bulb. So in this circuit, one of the bulbs would turn on, but the other one wouldn't. And so the punchline of this is that if your circuit is not working, there are usually two ways that it fails. One second. One of them is that there is an open circuit, so the loop that you thought was there isn't, or that there is a short circuit, which is to say that there's a loop that is there that you didn't expect to be.
We had an online question.
Yes.
Asking, does energy always take the shortest path?
Not necessarily the shortest in a sort of like physical distance sense, but it takes the path of least resistance, just like all of us do. And what happens in here is that it's basically lazy. Like if you think about it, like if it goes through here, it needs to do some work. If it goes through here, it needs to do some work to light up the bulb. And so it's going to take the option in which it doesn't have to do any unnecessary work.
I also had a question myself, and I might be going outside the realm of things.
I love going outside the realm of things.
So if this image, the first one on this slide, is
Yep.
the battery is a part of this closed circuit. Why do batteries die?
So what happens is that this. What makes energy move from one end of the battery to the other is chemistry that's inside the battery. And that chemistry in non-rechargeable batteries, the chemistry cannot be reversed, right? So what happens is that the battery gives up some of its chemical composition to create this energy. And then when that returns to the battery, some of that energy has been used up to light up the bulb or move the motor or whatever it is. And so the battery has been permanently changed and it has given up a little bit of itself to make somebody happy. And it does this for a few hours or a few days, and then it runs out of ability to do that, and then it's done. What recharging a battery does is, if the battery has chemistry that can be reversed, is you put it into a charger, and then the charger turns that backwards, where it feeds energy into the battery to reverse that chemistry. And now you put the battery back the way that it started, and the cycle of battery life repeats. Yeah. Yeah.
So what's causing the current to be following a path of least resistance in those two examples? Is like, as the closed circuit, it's working beautifully, but the short circuits, like, what's causing the short?
The energy knows. It's in the same sense that if you have a, let's say you have a waterfall, right? And that waterfall has it has like one side of it where the water can just drop straight down, and it has another side where like the water can, looks like it needs to spin a wheel, right? It is more favorable for this water to just drop down without going through the wheel. So that's what it's going to do. And you're going to find out that over time, unless you steer your water into your into the wheel, the water is going to go down the path of the least resistance. And so the cause there is that there is feedback, basically. Like if you hit the wheel, then like it bounces off and it can go in another direction. Whereas if it doesn't hit the wheel, then it doesn't have to do that. And so over time, like on the scale of waters, it drifts in a more favorable direction very slowly. Whereas in the case of electricity, the same kind of feedback happens where it tries going both ways, realizes that in one direction it's getting more pushback, where it would need to give up some of its energy, and then it redirects the other way. But in a circuit that happens on the order of milliseconds. If that's, was that a helpful analogy?
It is.
Yeah.
I guess I'm kind of wondering more about the root cause of that short circuit. Is it that the circuit could have been designed better to avoid that short?
Most commonly, the short circuits happen for two different reasons. Reason number one is that you're assembling a circuit and you either assembled it wrong where the instructions were wrong, or you've assembled it and it worked for a while, and then it failed in some way, often mechanical, that causes a short circuit. For example, if you drop your phone in the bathtub, that water that is in there basically acts as like a giant wire that all of this energy can flow through, and it creates short circuits everywhere in your phone, right? And so that is an example of, it could have been designed better, but you probably shouldn't have dropped it in the water, right?
Yeah.
And similarly, Ashley, when you were doing the repair at home, like you created a short circuit by touching two things that you were not supposed to touch together, and because you had a breaker, it didn't start a fire. But it wasn't that it was designed wrong, it was that it failed mechanically because somebody went in and moved parts around.
And actually, interestingly, one of the live wires was the three-way, and the other switch smoked.
Oh,
Yeah,
Got
so
it.
we had to replace that one too.
got
Good
it.
test.
I thought I saw a question in the back a minute ago.
Yes, I remember. So I'm wondering why, why is there, I feel like this was already explained, but just like, why is it accelerating so fast in a short circuit?
Why?
Comparison to like a closed,
Sorry, why? What's so fast?
the electrons.
Oh, yeah.
Yeah, they're like accelerating so fast in the short circuit.
Right.
And like,
Yeah. So that happens because in the case of a closed circuit, I mean, short circuit is a type of a closed circuit, just not the one that you want.
Yeah.
And the difference there is that the bulbs in this case are giving, they offer some resistance,
Oh, there is this.
right?
Thank you.
Yeah, and it's the resistance that slows down the flow of energy. And that is what keeps that energy from, say, overheating the wires and setting things on fire.
So then theoretically, if you use just no light bulb, just a closed loop wire,
Yes,
would that mean that it would go and would that be poses a virus as well?
absolutely.
Okay, cool.
Yes.
Thank you.
Now, to clarify that a little bit more, this goes back to the question about like safety and the things I was saying where like high currents and high voltages are more dangerous. It is difficult. It is more difficult to start a fire with something like a AA battery and a short piece of wire than with something like a wall power and longer pieces of wire and other switches in play. So that's one of the reasons why we limit ourselves in hobby electronics in terms of what we do to mitigate some of this. But if you think about all the times when people buy like a cheap power adapter for their phone that is not properly designed, this is the case of short circuit due to improper design. You plug one of those in and then it overheats and it sets your home on fire. That is an example in which you thought that you were being safe, but the device that you were using to provide you that level of safety between the more dangerous power that's from the wall versus the less dangerous power that your phone works on, it fails, and then it's at the point of failure, like in that charger, that you see fire starting. Yeah.
Is that what happens if your phone gets really hot?
That is
Like when you're charging?
that is actually a really excellent point for like 2 slides come on. So yes. Well, no, it's a really good question. Yeah. So yeah, let's see what does this adventure take us next?
All right.
Yeah. So basically, if you have a circuit that has to have some kind of power source, that's obvious, but we're saying, and most importantly, in whatever circuit you have, especially when you're just getting started, it's important to understand which power sources are relatively safe to work with versus the ones that will try to kill you in some way. And so power sources that are very forgiving for, especially for beginner work, would be anything that has a USB cable on it. So USB cables provide 5 volts and usually no more than 2 amps. And both of those numbers are pretty safe. And so it's very difficult to start a fire using what comes out of the USB cable. When a bad charger starts a fire, it's not on the side that like out to the low current and low voltage, but it's on the side that is plugged into the wall where the high current and high voltages are. And another power source that is very safe to work with are just regular AA, AAA batteries. They don't have enough energy in them to create any kind of like big problems. You can burn out an LED where the battery like that, but that's about the amount of damage that you can do. All the other common types of batteries, like coin batteries, like other kind of stuff, that's also pretty safe. But the ones that are the most commonly used are the AA and AAA. And then things that are dangerous, actually, as you learn, wall power, because it has high voltage and it can have high current. So you can get a lot of energy out of it, and it's really easy to start fires or to electrocute yourself. Thank you for not doing that.
No, it was just a tiny down.
Yeah.
I only had one thing.
Great. So it's really easy to hurt yourself. It's really easy to set things on fire with wall power if you don't know what you're doing. Just don't. And then the one that is a little more deceptive is lithium batteries, which are very common in consumer devices, like all our phones have lithium batteries in them. But working with them safely is not as easy as it might seem. And in particular, discharging them too quickly, so getting too much current out of them, or charging them too quickly, so pushing too much energy into them too fast, can cause them to overheat and start a fire. And so when your phone gets warm, but when you're charging it, it's because you're putting all this energy into the lithium battery, and the battery is heating up a little bit, and that's perfectly normal, that's perfectly fine. But if the charger malfunctions and it puts too much energy in, then the battery can overheat and start a fire. And one second, the thing that is particularly dangerous about lithium fires, and the reason why I don't think that lithium batteries is a good idea for beginner projects, is that you cannot put out a lithium fire with water. It requires a special type of fire extinguisher, because the lithium does not need to be exposed to oxygen to continue burning. And so if you have a big lithium battery, like maybe like in a scooter, and you have it like in your living room and it catches fire, it will burn your place down before you can, unless you happen to have the right kind of extinguisher, before the fire department gets there. Search for lithium battery
I
fires.
was gonna say, I think I saw that video.
Yeah, no, they're like some really terrifying. And so if you look at hobby electronics, you will see a number of reputable vendors selling reasonable lithium batteries, and I would not say no to using those, because they have made sure that the batteries are good. They have also made sure that the battery contains a circuit that prevents it from being damaged in that particular way. But it is not as safe as using a AA or a AAA. And definitely I wouldn't pick up a random lithium battery that I found lying around and put it in something that I was building.
Asking for a friend for a friend. What type of extinguisher is that? Lithium battery.
I wanna say has to be a Class C powder extinguisher, but I would have to double check. Yeah.
Years ago, when one of the Samsung Galaxy models
Yeah.
came out, like it was catching fire. I don't know if you remember that.
Yep, I remember that.
I'm assuming lithium battery inside,
Yeah,
not when it was being charged necessarily, but just when someone was using it.
yeah.
So what might have caused that?
A lithium battery can catch fire in two circumstances. One of them is if you're pushing too much energy into it while recharging it, and the other one is one is less common is when you're pulling too much energy from it while you're using it. And so if you don't design a protection circuit into it that prevents it from doing over discharge, is what it's called, then it can overheat while it's discharging. And so this takes us back to the earlier thing about short circuits, because a short circuit, what it does is it lets energy move very quickly through the battery and out of the battery and back into the battery on the other side. A short circuit can overheat the battery. And so if there was something as simple as like a loose wire somewhere inside the phone that would short circuit the battery, that is one way that you can set the lithium battery on fire.
I apparently have a lot of questions.
Yes,
Is this why?
this is actually the safety talk, and I'm really glad that we have a lot of questions.
Is this why electric cars are such a nightmare for fire?
Yes, that is exactly why. Because unless they bring the special fire extinguisher, the entire truck full of water is not going to put out the fire in the lithium battery.
And with the battery, well, and getting rid of them. Is also another barrier. The internet says Class B
Class B.
fires.
Great. Let's what's up next? I think try clicking somewhere maybe. There we go. Okay, great. So let's talk a little bit about how to make all this work, and how to keep your circuit from catching fire, but also how to make it work. So basically, what is happening here is that your power source, whatever it is, whether it's a battery or USB or like a different kind of power supply, it's going to output certain voltage. And you're going to know what it is in the sense that it's usually written on whatever you're dealing with. So for example, if I put one of these bricks somewhere on the bottom of it, is going to say something like 5 volts. And that is a thing that you cannot change. Your power supply brings its own voltage, and then you have to make sure that whatever is plugged into it can work at that voltage. So if I take something that is designed to work at 3 volts and plug it into a power supply that outputs 5 volts, that's not going to work. If I take something that's designed to work at 12 volts and I plug in a power supply that puts out 5 volts, that's also not going to work. The way that it fails is different. If you give something too much voltage, it will usually fail catastrophically, possibly create a minor like pop or explosion, like at these low voltages. And it will probably not be usable anymore. It's like burning out a bulb. If you give something not enough voltage, it usually just doesn't work. But sometimes if you give it not enough or kind of almost, it will just be kind of flaky. And so if your circuit is being flaky, usually one of the things you can look at is are the voltages actually compatible in the things that you're doing. This is one of the reasons why I think it's really important when you're just starting to follow tutorials that were written by people who know what they're doing, because that kind of tutorial is going to have the sharpness of parts that they actually work together. And then the other side of this, the current side of this, is completely opposite. In this case, the power supply is not what determines how much current is going to flow through the circuit. It is all the other stuff in the circuit that determines how much is going to flow through the circuit. So, for example, if I have a bulb that needs like an LED that needs like maybe 1/100th of an amp to operate, and then I take 7 of these and put together, it's going to take 7/100th of an amp to operate, and they're just going to try pulling that much current from the power supply no matter what. And the power supply either can supply it or it can't supply it. So if you have a look at again one of these bricks, you'll see that it says on it what is the maximum amount of current that it can output. And so now what happens is that if you have a circuit that asks for less than that, that works just fine. But if you make a circuit that asks for more current than the power supply is able to supply, then the power supply will fail in some way. And that can be various levels of catastrophic. If the power supply has some kind of a fuse built into it, the fuse might burn out, and then you can replace the fuse and get back to whatever you're doing. If the power supply is not protected like that, it might overheat and again, fire. Right? Yeah. And then, if you ask it for like a little more than it can give, but not too much, you can get into like my circuit is being kind of flaky problems again. And so the other thing that is worth checking if your circuit is being flaky is your power supply able to supply as much power as you ask it to give. And again, good idea to follow the tutorial to save yourself from this kind of problem when you're doing beginning. So, for example, if your circuit just has a couple of LEDs in it, you might see that they are flickering, or that one of them is on and the other one is off when both of them should be on. If you have a circuit that is supposed to do some kind of blinking light, they might be working too slow, or like they might be like intermittently flickering and some of them just turning off. Any kind of deeply mysterious, I don't understand why anything would ever behave this way, is a potential consequence of either voltage too low or current just borderline.
Like if the asking for too much current, it's gonna cause, like, could cause catastrophic damage.
Yeah.
Right? So let's say I have a 100-watt light bulb.
Yeah.
But for the brick, you know, you could buy like 60 watts.
Yeah.
When is it not light up? So like, oh,
it depends on the kind of a bulb. So if you're talking about like the old school incandescent bulb, what's going to happen with that one is that it will be dim. If you're looking at something like an LED, that one tends to have much more sort of either it works or it doesn't kind of behavior. So it might not turn on. So what ends up happening? So what ends up happening here is that in that particular case, if the bulb wants 60, if the bulb wants 100 and the power supply can only provide 60, it will probably not set the power supply on fire. What happens is that if the power supply can output 60, but the bulb is asking for something more like in the 65 to 70, then the power supply tries really hard. And in the process of doing that, it starts warming up. And in the process of warming up, it starts melting down and setting things on fire. Right? So it's like, that's why when it's borderline, it's much more likely to cause that kind of stuff. Were there more questions right now? Yep. Okay, all right. Let's keep rolling. Great. So now that we talked all about that, I want to talk a little bit about sort of like the life cycle of a circuit and how, like, you know, there are different levels of complexity, which also correspond to different levels of permanence, just in terms of how your project is put together. So, you can start with a piece of paper, and a pen, you know, and pen and paper, and draw a circuit on the paper, and that is that is definitely not going to set your house on fire. It also won't do anything, but it's really easy. It's really easy and it's really cheap to have to, you know, to do ideas in that kind of form. And many people, when they're talking about circuits, they were presenting with diagrams. You will, at some point, if you start doing mechanics, you will run into diagrams that other people have created, and then it becomes difficult to sort of be able to look at the diagram and realize that this is not like a photo of what your circuit is supposed to look like, but you can arrange parts so that they match what's in the diagram. So for example, if I have a single LED, for which the symbol looks like this, and I have a single battery, so that the symbol looks like that, and I put them up with wires, like so and like so. This is a diagram for a circuit that has a battery and an LED. And it is conventionally drawn such that all the lines are on straight and at right angles and all of that. But obviously that doesn't mean that you have to get wires that are bent at 90 degrees. And I know that this sounds obvious. You also will have to believe me right away that people have tried making their circuits look exactly like the picture on the paper and made their life very difficult without realizing that it was completely unnecessary. So then, the next thing that you can do is you can take your parts. Now, rather than drawing parts, you have some actual parts, and you can attach them to a thing called the breadboard. Now, what a breadboard does is it lets you plug things into it and then unplug them if you don't like the way you connected them. So it's really easy to experiment with. I'm going to plug this thing in over here, and I'm going to plug this other thing over here, and it will make it much easier to experiment with your circuit. So if you don't know how you want your circuit to be connected, you get some parts, you get a breadboard, you start playing around, and you probably won't set anything on fire. And the downside of doing that is that if you take a circuit and you put it on the breadboard and it starts working, that breadboard is not really holding things very firmly, so you can take your circuit and shake it, and things are going to start falling. So it's not a good way to make a circuit that is going to last a long time, but it's a really good way to prototype the circuit, to get it going where you understand what the connections need to be so that you can make it more permanent when you want to. Then the next step up is something called a protoboard or a fiber board. And it looks like a flat thing with a bunch of holes in it. And the advantage that it has is that now, instead of plugging things in and being able to unplug them, your parts get soldered into the protoboard. And soldering gives you a more permanent and more rigid way of attaching these electronic components to the board. And so once you have soldered them onto the board, like in the picture here, if you need to change anything, so if you need to disconnect parts or connect some other parts, it's much harder to do that because now you need to figure out how to redo your soldering. It's not as easy as unplugging and plugging back in, but you can take a circuit on a protoboard and you can shake it all you want, and probably nothing is going to fall out. And so now you have a circuit that is sort of like the next step of permanence. Is like you can take this and put it in a box, and it can sit there for a while and keep working. And you know, it's not going to fall apart when you're just looking at it. Once you get to doing this, once you do this for a while, what you find out is that your circuits end up being kind of weirdly constrained by these protoboards, in that you don't have enough control over the positioning of things on the board to make your circuit really small. And so as you get into wanting to make things more compact, because maybe you want to make something that you can really tuck away in a corner, now you're looking at making your own circuit board. You can do that sort of at a hobby level, which is a circuit board like this one. We have some LEDs and some chips on it. Now what you have done is you instead of having to by hand with solder make all of the connections, you actually take some of the connections between the parts and you make them part of the board itself. So now it's even harder to modify, but it's even more robust in just mechanical terms. And because now you have more control, you can make it even smaller. And then sort of like the final piece of this is when you're really doing sort of manufacturing at scale professionally, then you can have circuit boards that are made. For example, the circuit board that is made in a factory somewhere, where you send somebody else files for this is what I want my circuit board to look like. It's very similar to CNC stuff that you did for the last couple of weeks, where you do all the design on the computer and then you ship it off to somewhere and a thing comes back. And that is how circuit boards are done for everything that has a circuit board that you have, touched like in your life, is, large scale factory, but if you send your design to a factory like that, it usually takes them like a week or two before you'll even see anything. And so it's more expensive. That's even harder to modify because now you ordered, something and it takes 2 weeks for it to come back to you. And if you want to make any changes, now you're looking at another 2 weeks before you can see, what your revision said. So all of these things basically create a continuum where anybody that has worked on a circuit starts with a hand-drawn sketch and probably does some prototyping on the breadboard to make sure that their sketch makes sense and the circuit actually works. And then usually make the circuit more permanent by putting it on a proto board. And then depending on how far you want to take it, they might make either a hobby circuit board or they might order one professionally. Yeah.
So the mill, first of all, what's PCB?
Printed circuit board.
Printed. Okay. So with the milled PCB, where it says these can be turned into CNC tool paths, something like that, does that mean that the CNC machine is actually constructing the board, the PCB?
Yeah, and I'll tell you a little more about the details of how that works in just a second. What you got?
I was gonna ask you for PCB.
We do not have the right kind of milling machine for that, because we do have some capability to do milling in the machine shop, but milling circuit boards requires some additional things I'll talk about in a second that are mills out there. And the one CNC mill that we do have in the metal shop still does not really work for
Is that fair to say that most people will go from a surfboard to just ordering it from say China, like?
Yeah, it kind of depends on what your local maker space has. People who are starting, but if you are starting your own business making an electronics product, odds are that it makes sense for you to invest in a PCB mill. And so you will go and get one because what it does for you is that it makes prototyping much faster. You can make changes to your board and you turn it around within an hour or so and you see your changes board. And then once you've validated your board in-house with that kind of setup, then you can go from design files and ship them off to a PCB fabrication facility. And now you have much higher confidence that the thing that you get to later is actually going to work.
It's for like mass production.
Yeah.
When you order.
Yeah. I think mass in the sense of like the smallest order sizes are usually in the ballpark of 5 or 10. Some even down to 3, so you can get like as few as like 3 copies of the same circuit board for like not that much money, but still more money than you can soldering into a circuit board.
Last question.
Yeah,
The circuit board, they look like something that all electronics used back in like the 40s or 30s, like before milling machines.
Yeah.
Is that the case? Like
that is the case.
when did milled PCB like become a thing?
Bunch of Interesting question. I'm gonna tie all of these together into one very exciting answer, but before I do that, was there anything else that people want to? Okay. So I'm gonna digress for a second into the structure of PCBs, which is,
Permanent marker.
yes, okay.
Wow.
Which is also something that we're gonna talk more about, when we, you know what, let's talk for a second about what we're gonna do with the soldering process. So, what we're gonna do for, future, for when it comes to solder, is we're gonna split the process into one half get soldering this week, one half get soldering next week, but what we're doing for practice in the learning to solder part of this is we are assembling the kit. That thing, and I promise not to use too many parts. And, yeah, can you- Yep. But the kits have a tiny circuit board in it. So I'm gonna do is I'm gonna pull a couple of these out of the kit and then I'm gonna pass them down. So you can, yeah, you can put that one on Zoom. And then once you have it in your hands and you get a chance to look at it, it will make more sense for me to explain how circuit boards actually work on the inside.
I was gonna show you guys with my screen, but if I on-screen share, we're done forever.
Yeah, there's a picture of it in next week's slide. I think love if you can give me a photo. Or, you know what, even better. Slowly now the number browser. Good luck. I suppose so. All right, so, for people in Zoom, this is a picture of a different circuit board and, the diagram on the left is what I'm gonna go over. Historically, the way that circuit boards came together, is that we started with just a rigid board. And then, so the very, very olden circuit boards from like 60s, you would stick your parts through the board. So you drill the holes, and you would stick your parts through the board, and then you would still like run wires between these different parts. The purpose of the board was to give mechanical support to your parts, but it wasn't doing anything electrically speaking. And then the next invention in circuit board land was to take some kind of thing called a substrate, and then put a thin layer of copper on either side of it. So if you have a look at those circuit boards that we pass around, the way that they're actually set up is if you look at it in cross section, there's a thing on the interior that doesn't do anything electrically, just there for mechanical support, and there's a very thin layer of copper on the top and I think also on the bottom of these. And then what you do with that is now looking at it from the top. So let's say that your circuit board looks like but right. What you do with this copper is copper starts everywhere on the circuit board, but then you remove some pieces of copper from here. So let's say that I remove copper from like everything here in the middle and kind of over here. So now you have like some copper up here and some copper up here and some copper up here and some copper up here. If I leave copper between these two, if I leave copper between these two, what I have accomplished is I've made an electrical connection from this point to this point and from this point to this point, but not from here to there. And it is this selective etching of copper on the two sides of the board that basically took the wiring that used to be outside the board and folded it into the board itself. And that that was the big idea in making circuit boards. Is to take the wiring and basically bake it into the board by using these very thin layers of copper, one on each side of the board, and then selectively remove. That dates back to, I'll say like 60s going to 70s. And then the rest of it is basically just cosmetic, like, you put some stuff on the circuit board to like leave, like a little bit of text to tell people like, solder this part in here, et cetera, et cetera, et cetera. And we'll talk more about that when we actually do the soldering. But to answer the question was about like, why does the circuit board look brown? That seems very 70s. And some of these other things about like mass production and like why we do this way. The insulating layer in the middle that used to be brown and is now more commonly like clear to gray is just a different insulating material that we started building circuit boards with in I would say like 70s to 80s. And so the more modern material is not as friendly for working with at home because of its fiberglass. And so if you want to cut down your circuit board in smaller pieces because the project is smaller, you probably don't be cutting fiberglass at home because you only be inhaling fiberglass dust. And that is why your first board today that is intended for hobby use is still using the older circuit board material from the 60s because that material, even though it's not as great for like mass production, it is safer to use it. And then the process that has been used for etching the copper away from the board, as long as these boards have existed, has been basically a chemical etching, similar to glass etching. And it involves chemicals that are very home unfriendly. This is why etching boards at home is usually not a thing that people do. And it's like really hard to do in a safe kind of way. And so what ends up happening is that from a mass production standpoint, the etching process has always been what we have used. So even if you send a board out today to China, they're going to etch it using the chemical process. What milling does for the board is it gives you a way to accomplish something very similar without using chemicals. So now you start with a board that has copper on both sides, but instead of chemical removing the copper that's going on, you braid it away with a few units. And that is much more something that you can do at home and something that you can build into a device that is relatively safe to have at home. And so this is why PCB mills are more popular for hobby work than other ways of preparing circuit boards. However, it wasn't until maybe a few years ago that any kind of CNC thing at home was like reasonably difficult to do, just because of the cost of the machine and the component, et cetera. So it's only the last few years that we really see PCB mills for hobbyists being available. And to answer the last question about why it is that we cannot do this on the CNC mills that we have here, these boards are very thin, and as a result, they are somewhat flexible. So what ends up happening when you actually take one of these boards and you put it on a CNC, is that there's going to be some amount of flex in the board itself. And so the thing that PCB mills do that general purpose mills don't is that they have the ability to follow the surface of a board that might be slightly warped rather than assuming that the surface is perfectly flat. Because if you're working with like a hunk of aluminum, you can guarantee that the surface is out of aluminum is flat by machining it down. And you can't really do that with a fiberglass board that has a thin layer of copper here, because if you try to make it flat, then you're probably going to run the copper on the side. And so that's the reason why more control, like literally mechanical control, is needed to make these milling work compared to etching, because if you're just etching into the chemical, you don't care that the board is slightly warped. And so that's why we can't do it. That's why we can't do milling on the big machines that we have, because they're just not the time to do that kind of work on purposes that kind of money.
You know how much hobbyists PCB milling machine cost?
Order of thousands, but not tens of thousands of dollars. So similar to like other like CNC type of machines, they're even like a CNC router for home use in the older stuff. Yeah.
Where that would be beautiful more than popular.
Yeah. Yeah. Did I get one of those back? Yeah. Um, so if you have a look at this one, the orange lines on it are where copper was left and then it was just painted orange over for like decorative reasons. But if you were to scrape away the orange paint there, you would see, you would find like a very thin layer of copper underneath. The sort of greenish PCB color is very common for no particular different reason, but other colors haven't become more popular recently, and so when you get like some of these public kids, you'll see